Let's look at a 15-minute calculus problem today. So I'm going to try and get this done in 15 minutes here. So we're told in the question, according to Newton's law of cooling, the rate at which an object cools is proportional to the difference between its temperature and the temperature of the ambient environment, T sub A. Expressed as a differential equation, we get the derivative of temperature with respect to time is equal to K times T minus T sub A. All right, so I'm just going to analyze this for a little bit. First of all, ambient temperature just means the temperature of the surrounding environment. Think the room temperature. Also, the K in my equation here is my constant of proportionality. My guess is a little bit later on, and I can see in B we have a whole bunch of numbers that we're probably going to have to solve for K. Last thing here, this is the law of cooling. Now, you don't have to be familiar with the law previous to this because they give us the differential equation. It's just explaining what it is. Probably the only thing to understand really about cooling is for something to cool, it must be warmer than the surrounding area. Okay, so if I have something that is 100 degrees in an area that's 50 degrees, that 100 degrees is going to start to cool. Part A, we're asked to solve the differential equation, and we had a video on this before, so if you need to, you can go and check that out. But we're going to solve this differential, and we're going to solve it with respect to the temperature of the object after a certain amount of time has elapsed. So we're going to have to rearrange this a little bit. And we're going to let T0 be the temperature of the object when time is 0. Okay, and then in part B, we have an uninsulated cup of coffee cooling from 185 degrees Fahrenheit to 150 degrees Fahrenheit exactly 4 minutes after it has been served. The coffee shop maintains a room temperature of 75 degrees Fahrenheit. How much more time will it take for the coffee to cool to 95? And we're going to give the answer to 3 decimal places. All right, so we should be able to do this in 15 minutes. I'm going to start by solving my differential. So here's my differential equation, KT minus TA. Okay, now when we solve a differential, what we have to do is combine the like terms. We need all the capital T's on one side, all the lowercase t's on the other side. So let's go ahead and switch those around. I'm going to take my dt, and I'm going to move it up over here. I'm going to take all of this, and I'm going to move it down. So I'm going to get 1 over t minus ta dt is equal to k dt. All right, let's slide this up and give us a little more room. Now at this point here, we want to solve it, so we're going to take the antiderivative of each side. So this is one we need to know when we have 1 over something, that is the natural log. So I'm going to get the natural log of t minus ta. And on the other side, I'm going to get k with 1 lowercase t. This is where we're going to add that constant. Now, here's where we see the cooling idea. If t is bigger than ta, we actually don't need these absolute value signs in there. Okay. Now I want to rearrange this and just solve for this capital T. We want the temperature at any time. So I'm going to rearrange this, and I'm going to do that by using some exponentials. So I'm going to rate e raised to the natural log, and I'm going to do the same thing on the other side. So these two are actually inverse functions, so that's just going to leave me with t minus ta. Notice I've left off the absolute value signs, and we have e to the kt plus c. All right, this is probably the only trick here that we got to remember. I hate using trick, but the one thing we got to remember is those rules that we had for logs and the exponential. When things were added and subtracted, we can rewrite them as products and quotients. So I'm actually going to keep this side, But over on the right side, I'm going to rewrite this as e to the kt times EC. Now I'm doing that because this is just some constant. That is just C. Slide this up again. Now we got a couple of things to do here. We need to solve for C, so I'm just going to rewrite this with our C here. E to the kt times C. And we're gonna basically figure out what C is at this time. Now, if we go back to that question, we were told we're gonna let T0 be the temperature at time 0. So I'm gonna throw in a few T0. So that's the temperature now at time 0 when time was 0. And we have all of this. Now this is pretty good because we got k times 0 is just going to be 0. E raised to the 0, anything raised to the 0 is 1. So now we're left with C is equal to T0, the temperature that we start with, minus the ambient temperature. So we now have what C is. We need that constant, right? We're going to take those, that defined situation to find C. So now my final equation then for the temperature at any time is going to be T0 minus TA, that's my C part here, E raised to the KT, and I'm going to take all of this and move it to the other side, so plus TA. And there is our equation for the temperature of the coffee, in this case, at any time. 0, oops, sorry. Ooh. The question said how much more time? Okay, how much more time? So that would have been 13. And we're done. And if I look closely, that looks to be about the 15-minute mark. All right, let's take a look at part B. An uninsulated cup of coffee cools from 185 degrees Fahrenheit to 150 degrees Fahrenheit. The surrounding temperature of the room was 75 degrees Fahrenheit. How much more time will it take for the coffee to cool to 95 degrees Fahrenheit? So it's already been cooling for 4 minutes. How much? And it's gone to 150. How much more to get to 95? Okay, so I'm going to start with that formula that we just had. Its temperature at any time is the starting temperature minus TA, E raised to the KT, plus the ambient temperature, TA. All right, so here's where I said we do know the starting temperature, that's 185. The ambient temperature, that's 75. We have the temperature that we want to get to a little bit later is 95. Okay, we have our time, which is 4 minutes. So our problem is we don't know what K is. So we're going to have to use some information and find K. Okay, so let's go ahead and look at this first bit of information that they give us right here, and we're going to use that to find K. So we know that its temperature is 150 degrees after 4 minutes. So it started at 185. The room temperature was 75. E, we don't know K, but we do know the time has been 4 minutes. And the, again, ambient temperature was 75. So with that first bit of information, we have all of this, and our only unknown is that K value there. So we can rearrange this and solve for K. All right, so let's move all of that up and let's solve for K. So a little bit of algebra, we're just going to move some things around. I don't want that over here. So I'm going to get 150 minus 75. All of this here is giving me 110. E, I'm going to rewrite this as 4K. Okay, so again, left-hand side, do that, 75. We're going to divide off this 110. Oops, 110 e to the 4K. All right, now we have what we saw earlier. I'm going to need to take the natural log of both sides, because then the natural log and e, the inverse functions, just cancel each other out. So now I have the natural log of 75 over 110 is 4K. So if I divide this whole thing by 4, I can get K. Now in this case, I'm going to go to my calculator, punch all of that in, and I end up with, quite a big number here, but negative 0.09574 8, and that's probably enough. Later on I'm going to round this to 3 decimal places, but right now this is pretty good. Okay, so now let's roll all of that up. Don't know why that moved over. Okay, so now let's solve our question. So we want to get to a temperature of 95. I'm actually going to find the total time to find 95. So we're going to start at 185. And the ambient temperature was 75. E, well, we now know what K is, negative 0.09574 T plus, there's my 75 again. So it really looks the same, and now we're going to go through the same steps that we just did, and we're just going to solve for T. All right, so I'm going to start by getting rid of that 75. So this becomes 95 minus 75, so I'm going to speed this up. That's going to be 20. That is 110 again. I have E. This is probably the longest part, is rewriting all of this stuff. 748 T. I'm going to divide off this 110. And now at this point, I'm going to take the natural log of both sides. Again, natural log and E are going to cancel each other out. So I'm left with now the natural log of 20 over 110, so I can maybe speed that up and say 2 over 11 is equal to, oh my goodness, here's that big, all my time is taken up writing this number here. Okay, so divide this off. Negative 0.09574 So the time to get to 95, I punch that into my calculator, and I get the 17.805 minutes. All right, now I'm not quite done, because that's the time to go from 185 to 95. I already spent 4 minutes cooling to 150. So if I've already done 4 minutes, that means it's actually 13.085 minutes more to cool down, right? The question said, let's go back.